Hi, in the previous video, we have discovered what is a root mean square current and average power. In this video, we'll be talking about these two concepts of square waves and for sinusoidal AC. Let's look at example number 2. We are asked to calculate the power generated in a 5 ohm resistor when it's subjected to a constant current of 2 amperes and a square wave of peak value 2 amperes, which alternates between 2 amperes and negative 2 amperes. For the DC current of 2 amperes, we simply apply the formulas that we have learned before. P equals to I squared R. We know that the power is 20 watts. This is no problem at all. In part B, although the current reverses direction, the magnitude stays at 2 amperes. And since 2 squared is the same as negative 2 squared, giving the value of 4, we know that the power will stay at 20 watts throughout time. In fact, if we look at the current time graph for both of them and compare their I squared graph versus time, we notice that the I squared graph stays the same. Hence, it should be no surprise that the power given by I squared R is the same because the I squared values do not differ. At this point, you may ask me, why is there a need to learn about root mean square current? Well, so let's look at example number 3, where the square waves are slightly different. Notice that at 3/4 of the time, the current stays at I1, and the last quarter of the time, it stays at negative I2. And thereafter, it repeats itself periodically. We are first asked to find the mean square current in the resistor in terms of I1 and I2. Recall that the mean square current is the mean of the squared current. To solve the first part, we should square the current between time 0 and 3/4 t and square the current in the next 1/4 of time. And we notice that these are two values given, I1 square and I2 square. To mean this squared current, all we have to do is take 3/4 of I1 plus 1/4 of I2 squared. This is because in 3/4 of the time it remains in I1 square, and the other 1/4 of the time it remains in I2 square. In the graphical approach, we see that we need to square it, and the mean, by taking the mean, we would achieve this line. Graphically, what this means is that the area above the red line will be equals to the area below the red line. That is in effect what we are achieving by taking the mean of the squared graph. We are finding a value where the areas above it will be equal to the areas below it. In part B, we are given the values for R, I1, and I2, and we are asked to find the average power. Since the average power is simply the mean squared current times R, all we have to do is sub in the values and find that the power is just 65 watts. Next, we are asked to find the root mean square current. The root mean square current is simply the root of the mean square current. So you substitute in the values, we will get square root 13, which will be equals to 3.6 amperes. Graphically, what this means is that we need to first square the current to achieve the current square versus time graph. Notice that I1 becomes I1 square, I2 becomes I2 square. We need to then take the mean such that the areas above and below are the same. We need to then to the root. Right? We need to square root this mean value to find the root mean square value. So what you have here in this green line is the root mean square value. Next, let's look at what the average current is. To average a current, since the current is 3/4 time in I1 and 1/4 time in I2, by substituting in the correct and appropriate values, we find that the average current is 2.5 amperes. Note that this value of 2.5 amperes is lower than the root mean square current. That is to say, if you were to wrongly use the mean current, square it and multiply it by R to find the power, you would be underestimating the power provided to the object. This is in fact a dangerous exercise, which I will illustrate later on with examples. Next, now let's look at the sinusoidal AC, which is in fact the more important waveform that occurs most of the time in this topic. Sinusoidal waveform looks generally like a wave, and the equation describing it is given by I equals I naught sine omega t, where I naught is a peak value and omega is the angular frequency and t is the time. So to find the root mean square value, we need to square the current versus time, and we find that the current square is I naught square sine square omega t. At this point, it's still simple mathematics. Because now you all use graphic calculators, you can in fact simply key in this value and plot it and be able to find the I-square graph. However, for learning, let's look at how we can draw it without a graphic calculator. So if you look at the sine square graph, there we have some difficulty in plotting sine square graphs because we do not know how it will actually look like. We know how to plot a sine curve, we know how to plot a cosine curve, but square curves are much more different. But notice that we can manipulate sine square omega t into half multiplied by 1 minus cosine 2 omega t. Alright, simply because cosine 2 omega t is sine square omega t plus cosine square omega t. So let's start with a cosine omega t curve. The cosine 2 omega t curve will be double in terms of frequency. The period will be half, and hence we can achieve the purple graph. We want a negative cosine 2 omega t curve, hence we will achieve the red curve. So all these things that I'm doing now is actually curve sketching and curve manipulation skills. If we want the 1 minus cosine 2 omega t curve, we should have to move the curve up by 1, and we will arrive at the blue curve shown here. If we want then the I square graph, which is I naught square sine square omega t, we simply multiply the previous curve with half I naught square, and we hence arrive at this value, where the peak value is I naught square. Now, back to the main flow of the topic. We are given the I current versus time graph. We square it, we get the I square versus time graph, as I've shown before in the previous slides. Notice that in the previous graph on top, current completes itself in one cycle in period t, but in the I square graph, two humps give you time t. It's important that you do not make the mistake of thinking that one cycle in the I-square is a period. In fact, it is 2 cycles in the I-square graph that gives you a period. To find the root mean square again, we have to square it, mean it, and root it. So after squaring it, we have to find the mean. Taking the mean, we will have to confirm that the top area is in fact equals to the area at the bottom, and that these two areas must be the same. We can repeat this for all areas and show that they are the same. One more time. And we notice that the mean value of the I-square graph is simply half of I0 square, since the peak value is I0 square. This is due to the symmetricity. This is due to the graph being symmetric along this line. After taking the mean, we have to square root it. Since the mean value is half I0 square, the root mean square value will simply then be I0 over square root 2, provided by the green line, provided by the yellow box with the formula. So one more time, the mean value is symmetric. It's the line that causes this graph to be symmetric, right? We've seen that I square versus t is symmetric about the middle value. Hence, the mean square current for a sinusoidal AC is half I0 square. And the root mean square current given by square root of the mean square current is I0 over square root 2, which is approximately equals to 0.702 I0. At this point, if you're confused by everything that I've said before, this is the one equation that you have to commit to memory. Right? So the root mean square current, one more time, is the peak value I0 divided by square root 2. Hence, we can derive also the root mean square value for voltage to be V0 over square root 2, and the average power. Notice that for average power, it's mean square current times R, since root mean square current squared is simply the root mean square current squared here, so it's I0 over square root 2 squared, which gives us I0 squared R divided by 2. I0 squared R is the peak current squared times R, which gives us the peak power. This simply means that the average power is the maximum power divided by 2. This is another key point that you have to remember. The other important point is that these equations, these 3 equations that I've boxed in yellow, are only true for sinusoidal waves only. If you apply this to square waves, you'll be gravely mistaken, right? And you will be ultimately sad. So let's look at work example number 4. The voltage of the electrical power that we use daily for electrical means is 240 volts. We all know this, but do you know that the value given is actually a root mean square current? Now you know. We are asked to find the peak voltage available from these electrical mains, and we are asked to calculate the root mean square current for electrical kettle boiling, for electrical kettle with a power rating of 1000 watts. The root mean square current is simply V0 over square root 2, and hence the peak voltage V0 is 200 multiplied by square root 2. We get V0 equals to 340 volts. The average power dissipated is VRMS multiplied by IRMS, as we have proved in the previous slides before. Since we know the power rating, to be 1000, we can simply sub in 1000 as the mean power. Notice that the ratings given for electrical appliances are and will be the mean power. Do not confuse this for the peak power. The mean power for electrical appliances that work on AC are the mean power. So if I tell you that a hair dryer has 500 watts power, it means that the mean power is 500. Since the mean power is given by VRMS multiplied by RMS, we can simply sub in 1000 for the power, 240 for the VRMS, and find that the IRMS, the root mean square current, to be 4.2 amperes. Example number 5. A tourist takes an electrical water heater designed to operate with 110 volts electricity to Singapore. This means likely that this tourist is American, or that he bought an American-based water heater. He plugs it into a 240 volts outlet and the heater breaks down due to overheating. Let's find out why. So in part A, the heater normally consumes 500 watts of power. What is the resistance of the heating coil? So it means that the average or the mean power of the heater should be 500 watts. And if it works with 110 volts electrical supply, it means that the VRMS that it should work with should be 110. That way, we are able to calculate the resistance of the water heater and find it to be 24.2 ohms. If we then plugs it into our 240 volt supply, remember that the resistance of the object does not change. With the new VRMS of 240, we find that the power given is in fact 2380 watts. This is four times the power that the heater was designed to work with. So it's not surprising that the heater breaks down. Next, what is the root mean square current that flows when the potential difference is 240 volts? Since V equals to IR, and V and I are in phase, assuming that the water heater is a pure resistor, we have current equals to 240 volts divided by 24.2 ohms, giving you 9.9 amperes. Example number 6. A sinusoidal alternating current is described by this equation and it's flowing through a 12 ohm resistor. Find A, the root mean square value of the current, and the voltage across the resistor. Notice that in this waveform equation, 9.0 will be the peak current because the maximum value of sine omega t is 1. So to find the root mean square current, all we have to do is apply the formula of IRMS equals to peak current divided by square root 2. Substitute in the value of 9 and we find that RMS is 6.4 amperes. The root mean square voltage is simply the root mean square current multiplied by R. Since we have already found the IRMS before, substitute in the correct values, we simply get V is equal to 76.4 volts. In part B, we are asked to find the maximum instantaneous power. Maximum instantaneous power is given by P naught. P naught then is equals to the maximum current square times R. Since the maximum current is 9, resistance is 12, applying some simple mathematics, we get that the maximum power is 972 watts. In part C, we are asked to find the average power in the resistor over time. Since the average power is given by IRMS squared times R, and we have calculated IRMS previously to be 6.4. We find that the power, average power, is 486 watts. Note, this is an important point, that the maximum power and the average power is related by this equation. The average power is simply the maximum power divided by 2. In part C, we could have simply calculated the average power as half of the maximum power if we have remembered this equation. So there are more than one way to reach the result. You could calculate it by taking half of the maximum power, or calculate the average power from root mean square value. However, the point here is that this can only be true that P0 over 2 is the average power only if the wave is sinusoidal. Now, sketch a graph to show how the power varies with time, assuming that omega equals to 100 pi. The power dissipated in the resistor is given by this formula. Simply reduces to 972, the peak value, sine square omega t. To plot sine square omega t, you could just simply key it in your calculator to graph it. Or if you remember what I've taught you before in curve manipulation, you can plot this graph. Note that the period can be found using omega to be 0.02 seconds. And once again, note that the period of 0.02 seconds occurs after the power completes 2 cycles. This is still the period, because the period is considered as the time taken for the current to complete a cycle, not the power. Right? So 2 cycles of power is equals to 1 period. Notice also that the peak power is twice the value of the average power. Okay, and all these are true only for a sinusoidal alternating current. Right, so to end off, this is a summary of all the equations that I've taught you until now. For a direct current of value I0 and an alternating current of maximum current I0, we have the root mean square value of the DC being I0, the mean power being P0 for DC. For sinusoidal AC, the root mean square current is given by I0 over square root 2, and the mean power is just P0 over 2, the maximum power divided by 2. In the next video, I'll talk about transformers. So see you then.